Excuse me. Greetings, Saints. Maybe on lesson 6.5, which is regarding indirect proof and triangle inequalities. Indirect proof is a rather fascinating exercise for us to tackle right now. Because what we're going to wind up doing is that it's different from what we've done so far because we're going to prove what things are by proving what they are not. So you have to consider the binary instance of something being true or false. Um, or sometimes that there's going to be only two alternatives. So, for example, let's say that there's only two alternatives for Mr. Granados as a teacher. Mr. Granados is a good teacher, or Mr. Granados is a bad teacher. Now, is it possible to prove that Mr. Granados is a bad teacher by, in this binary instance, by proving that he's not a good teacher? That would logically then leave only the choice that he would be bad, right? So this is how this works with indirect proof, is that we're going to prove the truth of something by showing what it isn't. Okay, so here we go. We're going to start here. A little two-column proof, same way that we've done previously. So I'm going to have lines L, M, and N. And then I'm going to have some angles here, which I'm going to have 1, 2, and 3. And here's what we're going to actually wind up showing here is that we're going to have this given, right? Where we're going to have line M, and we're going to say that it's not parallel to N. And what we're going to prove effectively is that we have angle 1, which is going to be not congruent to angle 3. So the methodology for doing an indirect proof, two-column, works as follows. So we start off our two columns, right? And we have our left, which is our statements, and our right is which is our reasons. But it's going to work out differently because where we've started with step 1 is we've typically just taken this given with 100% of our proof so far and redone this, where this is our statement right here, and then the reason why is because it's given on step 1. That's no longer what we're going to do here. Instead, we're going to prove and make an assumption about the opposite case being true. Okay? And then when we do that, it's going to then indirectly, in reverse, prove what's given here. So what we wind up doing here is this, is that we're going to say, take this statement, which is angle 1, congruent to angle 3, and say that this is instead our assumption, or that we assume. Okay? So we take the proof statement, and we're going to make that our first statement and assume. So where we've typically before restated what's given, and that's our reason, instead we take the proof step, take the logical opposite, and make that our assumption. Now, what do we know about angles 1 and 3? Well, angles 1 and 3 are corresponding angles. All right, and if they're corresponding angles, reason we can say that is because of the definition of corresponding angles. And since we have a theorem for that, right, which was that if we have corresponding angles are congruent, that the lines that are formed off of that transversal will be parallel, okay? So M then would have to be parallel to N, and that's because of the two parallels that are cut by the transversal. So you see, it's kind of like in reverse, and we take that logical opposite to get make these conclusions. All right. Kind of an interesting exercise for us to take. So here's why we actually go ahead and do this, and it's for when you have an exercise like the following. In your textbook, excuse me, in your textbook, it's done abstractly with letters A, B, and C, but I'm going to give you guys some actual numbers so that this, I think, makes a little bit more sense to you. And that it just not isn't going to be so you'll be able to instantly recognize this with using numbers. So, for example, if we have the number 10, which is equal to 6 plus 4, okay, and 10 is greater than 6. I'm sorry, then 10 is greater than 6. And 10 is greater than 4. Now, I think some of you guys are seeing that and you're like, yeah, no kidding. So this supposition, if 10 is equal to 6 plus 4, which it is, right? That's absolutely true. It's a true statement. Then, of course, it's going to be equal to 6 is greater than 10. That's a fact. I'm sorry, 10 is greater than 6. That's a fact. And 10 is greater than 4. Also another fact. But the reason why, though, is because any number, what we're saying, is going to be greater than the sum of the individual parts that make it. All right? So here's how we're going to actually utilize this. Let's actually draw the following diagram. Right. Then here we have some angles. We have angles 1, 2, 3, 4, and 5. And for these angles, what we're curious about is what angle has the greatest measure. And it is not enough for you guys just to eyeball it, right? And just say, oh, it's the biggest, right? No, 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 no. Why, logically speaking, is one going to be, and I think that's our instinct says that that's going to be the biggest one. But why logically is that going to be the case? Well, here's what we are given as facts. We know that angles 4 and 5 are perpendicular to each other because it's just marked that way. Therefore, if that's the case, we know the angle measurements for 4 and 5 are both 90 degrees. All right. So now through theorem, we have this right triangle, and we actually just discussed this, that we have these two, and not theorem, actually, it's a corollary. Specifically, we had the theorem about the interior angle sum for a triangle, but for a right triangle, we know these two acute angles have to be complementary. That was the corollary that we had. So, if they're complementary, then we know the following. It has to go back to this, right? That the sum of 2 and 3 would be 90. Therefore, each of those would have to be less than 90 individually. Angle 2 and angle 3 would both be less than 90. Right? Because they're the sum that makes up the complementary angles. Okay? So, another fun fact here is, again, we have angle 1 with 4 and 3. Well, think about this. It means that angle 1 is going to be equal to the sum of 3 and 4, or 4 and 3. Why? These are exterior angles, right? It was the exterior angle, angle 1, is going to be equal to the sum of the two remote interior angles. All right? So what I can say then is that measure of angle 1 is greater than measure of angle 3, right? Because of this. Anything's going to be greater than the sum of the little parts that make up the angle, or make up the sum. So 1's greater than 3, 1's greater than 4. And then, because we know 4 and 5 are both 90, it means they're congruent. So then 1 also would have to be greater than 5, because it's already greater than 4, and 4 and 5 are the same. And then we only have one more of these angles to discuss, right? We have 1, it's greater than 3, greater than 4, it's greater than 5. And then what else is going to be greater than? Well, it's going to be greater than angle 2, okay? Again, this is because angle 4 is congruent to angle 5. And then this was back because of the interior, or the exterior angle sum, right? And 2 is a lot of things we could say. Well, 2 is less than 90, so it's going to be, means 2 is going to be less than the measure of angle 5, right? So of course it's going to be less than the angle 1. All right, next. Let's discuss the angle side relationship. In a triangle, it's effectively this. It's the biggest side is opposite the largest angle, and the small side is opposite the smallest angle. All right. So, here we go. Let's go ahead and illustrate this for you guys. I got a triangle. It is A, B, C. All right. So what we're saying is if AB is greater than BC, all right, this guy greater than this guy, well, it's the side opposite. So this is where some of you guys have struggled with the difference between a side and an angle, and some of you guys got to sort out right now. The relationship AB is opposite angle C. So this is going to be the larger, right? And then we have BC, which is opposite angle A. Because it's dictated by what it is opposite, right? If AB is greater than BC, then angle C is greater than angle A. Moreover, if I were to take the following, I have angle or sides A, B, C with dimensions 11, 12, and 13. Okay, so what we're going to do here is we're going to list the angles from least to greatest. So, from least to greatest, we need to find the least side, that's AB, and that's opposite angle C. All right, next is the 12, which is opposite angle A. And then the 13 is opposite angle B. So C is the least, A is the middle, B is the greatest. All right. Hope you guys are hoping for a lot of these types of problems. All right. So now kind of where we get to why indirect proof is kind of handy and kind of what things can be, because we're going to start to work with stuff that's a range of values. Because we'd like to be able to figure out dimensions of a triangle and know what something can be. Like, can we know just based upon the angle or the measurements of the sides what the angle measurements are? Well, we can at least ballpark it about what's going to be the biggest and smallest. But what's kind of the range of values? So here, let's actually discuss the triangle inequality theorem. So let's go ahead and write out another triangle. And here's how the triangle inequality theorem works. It's this. The range of values and what's possible in a triangle. It's that the sum of any of the two sides will always be greater than the third side. Okay? So AB and BC would have to be greater than AC. And this has to be true for every single side. So AC and BC would be greater than AB. And AB and AC would have to be greater than BC. Every single one of these must check out for this to work. So let's actually put this into practice. All right, let's draw another triangle here. And it has sides of 20, 12, and x. All right, so the triangle inequality theorem would say this, is that we're going to take two of the sides. X plus 12 would have to be greater than 20. We'd have x plus 20. It's got to be greater than 12. And then 20 plus 12 has got to be greater than x, that third side. Now, one of these statements is going to wind up being redundant, right, as we go through here. And we're going to have to solve each of these values, okay? So for this guy right here, what it means is that we're going to subtract 12, okay? So one of the things we know is that x for sure has to be greater than 8, okay? Now, if I subtracted 20, I'm going to say that I'm going to have a side that's got to be greater than, x has got to be greater than negative 8. And this is an extraneous statement. It's kind of silly. Of course it would have to be greater than negative 8. In fact, it's impossible. What we're saying then is that side could potentially be negative 7, right? Because negative 7 is greater than negative 8. Or 0 is greater than negative 8. But that's impossible to first have a side length that's going to be a negative number. So we're going to go ahead and eliminate that. Now, 20 plus 12, that's going to give me 32, is greater than x. And what I'm going to do is take these two and write a combined inequality. Is that 8 less than x less than 32? I think you guys maybe remember this from pre-algebra. right? Where it works on the number line. And these are the possible range of values for this third side x, is that that third side is going to be anywhere between 8 and 32. And we'd have to do this. Like, it's, for example, not going to be 8. It can't be 8. It's impossible. Because what we're saying then is, if you just put 8 and 12 next to each other, it's not going to match up to that third side, right? You even imagine an 8-inch ruler and a 12-inch ruler, and then matching it up to, well, 8 and 12 is 20 on the dot, and that's going to overlap and be even with that entire third side. Okay, so that it can't even work. And then the other part being like with 32, right? With the 20 and the 12, um, same sort of thing, right? With 20 and 12, and then 32 side by side wouldn't match up with that third side. And I can show you guys a visual in class here. Okay. Um, Last but not least, we have some range of values here, and you guys are going to tell me if these triangles are even possible. So let's do a few of these here. We have 4, 9, 10. We have 8, 9, and 18. Okay. And then we have 5, 12, and 17. I'm sorry, and 20. Actually, let's make that 17. Okay. So we're going to see if this is a possible triangle, right? So we have to check every single statement. So 4 plus 9, is it greater than 10? Yes, that's 13, greater than 10. Is 9 plus 10 greater than 4? Well, both values are greater than 4, so that for sure is true. And is 4 plus 10 greater than 9? Well, yes, so this one is true. This is a possible triangle. Now take this guy. If I do 8 plus 9, is that going to be greater than 18? That is not. So that is false. And now we don't even have to check any of the other values, right? Because even if 9 plus 18 is greater than 8, which it is, because one of the values didn't work, it's automatically going to be false. We can't prove it any more correctly. And then here we go. 5 plus 12 greater than 17. Well, it's equal. So this one is also going to be false and not a possible triangle. Okay. This is our only possible dimensions for a triangle. I will see you guys in class. I'm going to go ahead and get this posted to Canvas. If you have questions, see me during office hours. Thanks.